Hi everyone. Today we'll be discussing the power series, radius, and interval of convergence. So we're going to understand the definition of power series, find the radius and interval of convergence of a power series, determine the endpoint convergence of a power series. The definition of a power series. If x is a variable, then an infinite series of the form summation of a sub n x raised to n for n is equal to 0 to infinity is equal to a sub 0 plus a sub 1 of x plus a sub 2x squared plus a sub 3x cubed until an a sub n x raised to n as n approach infinity is called the power series centered at 0. So if you can recall, you can have your Taylor series as x minus a raised to n. So this is your a sub n x minus a raised to n, where a is the center. More generally, an infinite series of the form summation of a sub n x minus c raised to n equal to a sub 0 plus a sub 1 x minus c plus a sub 2 x minus c squared plus and so on and so forth until a sub n x minus c raised to n is called a power series centered at c, where c is any constant. So this is derived from Maclaurin's, while the center at c is derived from the Taylor's polynomial. A power series centered at 0. Let us consider a certain power series centered at 0. So we have summation of x raised to n over n factorial is equal to 1 plus x over 1 plus x squared over 2 factorial or 2 plus x cubed over 3 factorial. If we have a power series centered at -1, we can have, for an example, -1 raised to n times x plus 1 raised to n. So, since we have x plus 1 equal to 0, so the center is located at -1. So, we have 1 plus x plus 1 plus x plus 1 squared minus x plus 1 cube and so on. A power series centered at 1. So, x plus 1. This is x minus 1 equal to 0. So, the center is at 1. As an example, we can have 1 over n, x minus 1 raised to n. So, that would be 1 over 1, x minus 1 raised to 1. Plus 1 half x minus 1 squared plus 1/3 x minus 1 cube and so on. These does not really refer to any particular function, but these are examples with different centers. A series of the form c sub 0 plus c sub 1x plus c sub 2x squared plus c sub n minus 1 x raised to n minus 1, where x is a variable and the coefficients c sub 0, c sub 1, c sub 2 up to c sub n minus 1 are constant, is called a power series in x. A power series in x may converge for all values of x and for no value except at x is equal to 0. Or it may converge for some values of x and diverge for other values. The totality of values of x, which the power series converges, is called the interval of convergence of the series. This interval of convergence can be determined by the ratio test through the cases where the series does not converge for all values of x. The endpoints of the interval must be examined separately using the other convergence test. The series converges the series converges absolutely for all real values of x. This theorem states that the convergence is set from negative infinity to positive infinity, and the radius of convergence or the radius of converges is positive infinity. That is, r is positive infinity from 0 to infinity. So that's the radius. So it is defined for all real numbers. The series converges absolutely for all x in some open interval from negative r to r, and diverges if x is less than negative r or x is greater than r. This theorem states that the convergence set extends between negative r and r, and the series has the radius of convergence r. That is, r is equal to r. The interval and radius of convergence is illustrated below. So there is a specific value uh, that bounds the convergence of the series. So it only converges in between these two values of r. If a numerical value is substituted for x in the power series c sub k, x raised to k, then the resulting series of numbers may either converge or diverge. This leads to the problem of determining the set of x values for which the given power series in x converges, and this is the convergence set. For any power series in x, exactly one of the following is true. The series converges only for x equal to 0 or at the center. So one possibility is it only converges at the center. This theorem states that the convergence set for a power series in x always an interval centered at x is equal to 0, and the radius of convergence is 0, that is r equal to 0. The interval and the radius of convergence is illustrated below. So there is only one value that would make the series converge, and that is at the center. As an example, find the interval of convergence and the radius of convergence of the following power series. Let us consider the summation of x raised to k for k is equal to 0 to infinity. So this means that we will be having x raised to k. So that would be 1 plus x raised to 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth, and so on. So the general term a sub k is equal to x raised to k. So we can try to check for the convergence of this series, of this power series, by applying the ratio test. So rho is equal to mu sub k plus 1 over mu sub k. So that is x raised to k plus 1 over x raised to k, because a sub k plus 1 is equal to x raised to k plus 1, and a sub k is nothing but x raised to k. So your rho is the limit of your a sub k plus 1 over a sub k as k approach infinity. So this would be x times x raised to k, or x raised to k plus 1 over x raised to k. And we're going to evaluate the limit as k approach infinity. So this is x. So the series converges absolutely if rho is equal to x less than 1, and diverges if rho is the absolute value of x is greater than 1. The test is inconclusive at x is equal to 1. So taking note of the rules for ratio test, um, if rho is less than 1, it converges. And if rho is greater than 1, it diverges. And inconclusive at the endpoints. So meaning we can have the value of x from negative 1 to positive 1. So we have now to check whether the boundaries would make it diverge or converge. So if we're going to consider the boundary at 1, so it would be 1 plus 1 plus 1, and it would be approaching infinity. So the sum is divergent. Now for negative 1 raised to k, so 1 minus 1 plus 1 minus 1, so the value of the sum diverges in between two possible values, 0 and 1, so it is a divergent series. So it is possible that the sum would be 0, or if it ends here, the sum would be 1. So there's no unique value, so this is not approaching 0. For an alternating series, the last term should be approaching 0. So this is not approaching 0. So this is a divergent series. So thus, 1 and negative 1 would not make it convergent. So thus, the interval of convergence is from negative 1 to positive 1. And the radius is from 0 to 1. So the radius is 1. So if this is your center of convergence, the radius of convergence is r equal to 1. And it would be from negative 1 to 1, the interval of convergence. So since negative 1 and positive 1 is not included, so we have the radius of convergence from negative 1, as the interval of convergence from negative 1 to positive 1. Now let's have another example. Find the interval of convergence and radius of convergence of the following power series: x raised to k over k factorial. So we're going to apply ratio test. So your a sub k plus 1 is x raised to k plus 1 over k plus 1 factorial. And your a sub k is x raised to k over k factorial. For rho, we divide a sub k plus 1 over a sub k. So that would be x raised to k plus 1 over k plus 1 factorial divided by x raised to k over k factorial, evaluating the limit as k approach infinity. So this is the limit as k approach infinity of x times x raised to k over k plus 1 times k factorial, multiplying it by the reciprocal of the denominator, so k factorial over x raised to k. We can cancel out x raised to k and k factorial, so the answer is the limit as k approach infinity of x over k plus 1. So this is approaching 0 because as k approach infinity, for whatever value of x, not infinity, so it would be approaching 0. So since rho is less than 1 for all x's, the series converges absolutely for x. So all values, so it means from negative infinity to positive infinity, and the radius of convergence is positive infinity. So just to visualize that, the center is at 0, and it would be from negative infinity to positive infinity. For our third example, find the interval of convergence and radius of convergence for the following power series: k factorial x raised to k. So for this one, your a sub k plus 1 is equal to k plus 1 factorial x raised to k plus 1, and your a sub k is k factorial x raised to k. So for rho, it is the limit of k plus 1 factorial x raised to k plus 1 over k factorial x raised to k as k approach infinity. We define k plus 1 factorial as k plus 1 times k factorial, and we define x raised to k plus 1 as x raised to k times x raised to 1 over k factorial x raised to k. So we can cancel out x raised to k and k factorial. So we now have the limit as k approach infinity of k plus 1 x. So this is, as k approach infinity, this would be infinity, which is greater than, which is approaching infinity. So therefore, this is always divergent. So therefore, the series diverges for all non-zero values of x, and thus the interval of convergence would just be for x is equal to 0, the center of convergence. So it is only at x is equal to 0 that the series converges, and the radius of convergence is r equal to 0. Let's have additional examples. So find the interval of convergence and radius of convergence for the following series, for the following power series. So your a sub k plus 1 is x raised to k over 3 raised to k times k plus 1. Sorry, this is our a sub k. And our a sub k plus 1 is x raised to k plus 1 over 3 raised to k plus 1 over k plus 1 plus 1. So we solve for rho, which is the limit of a sub k plus 1 over a sub k as k approach infinity. So it would be x, so limit as k approach infinity of x raised to k times x over 3 raised to k times 3 times k plus 2 times a sub k. So we check for the reciprocal, 3 raised to k times k plus 1 over x raised to k. So we can cancel out x raised to k, 3 raised to k. So we have the limit as k approach infinity of x times k plus 1 over 3 times k plus 2. So this is would be an infinity over infinity. So we apply L'Hopital's rule. So that would be x over 3. So applying L'Hopital's rule, it would be 1 over 1. So when x over 3 is less than 1, this would be convergent. And when x over 3 is greater than 1, it would be divergent. So we have x is in between negative 3 and positive 3. So that's why we have the interval of convergence to be from negative 3 to positive 3, and the radius of convergence is at 3. Now we have to check at the boundary what would happen. So we try to check at -3 and +3. So we have -1 raised to k at +3. So we have 3 raised to k over 3 raised to k times k plus 1. So we can cancel out 3 raised to k. So this becomes -1 raised to k over k plus 1. So this is an alternating series. And this is decreasing. This is decreasing and it is approaching 0. So it is convergent. So +3 is included. So we can include +3. However, when k is -3, so at k is equal to, at x is equal to -3, so we have -1 raised to k, -3 raised to k over 3 raised to k times k plus 1. So -1 raised to k times -3 raised to k is 3 raised to k over 3 raised to k times k plus 1. So this is 1 over k plus 1, which is somewhat similar to a harmonic series, which is divergent. So that's why -3 is not included. So it is an open interval at -3 and closed interval at +3. Let's try for our last example. Find the interval of convergence and radius of convergence of the following power series. So we have 3 raised to k, k factorial over x raised to k. So let's have your a sub k plus 1 will be 3 raised to k plus 1 x raised to k plus 1 over k plus 1 factorial. While a sub k is 3 raised to k x raised to k over k factorial. So our rho is equal to the limit as k approach infinity of a sub k plus 1 over a sub k, which is the limit as k approach infinity of x a sub k plus 1. So that's 3 raised to k plus 1 x raised to k plus 1 over k plus 1 factorial divided by 3 raised to k x raised to k over k factorial. We simplify this limit as k approach infinity of 3 raised to k times 3 x raised to k times x over k times k factorial times k plus 1 times the reciprocal k factorial over 3 raised to k x raised to k. We can cancel out k factorial, 3 raised to k, and x raised to k. So what's left is the limit of 3x over k plus 1 as k approach infinity. So this is approaching 0 because we have 3 over infinity. So 3 divided by infinity, so that would be approaching 0. So meaning it is always convergent. If it is always convergent, so centered at 0, so we have the radius of convergence is positive infinity and the interval of convergence is from negative infinity to positive infinity. For a power series centered at C, precisely one of the following theorem is true. The series converges only at C, only at the center. If the series converges only at C, the radius of convergence is R equal to C, and the interval of convergence is C, is 0. So the interval and the radius of convergence is illustrated here. So it diverges at any value aside from x sub 0. So the radius of convergence is 0 and the center of convergence is at x sub 0 equal to C. There exists a real number r greater than 0 such that the series converges absolutely for x minus c less than r and diverges at x minus c greater than r. This theorem states that the convergence set extends between negative r and positive r, and the series has a convergence, and the series has a radius of convergence of r. The interval and radius of convergence is illustrated below. It is centered at x sub 0, and plus r, it would be the radius of convergence, or minus r. The series converges absolutely for all x's. So if the series converges for all x, the radius of convergence is r equal to infinity, and the convergence set is from negative infinity to positive infinity. Determine the radius of convergence and interval of convergence for the power series. Negative 1 raised to n times n over 4 raised to n times x plus 3 raised to n. So the center is at x equal to negative 3. So for ratio test, we can have your a sub k plus 1 equal to k over 4 raised to k times x plus 3 raised to k. So plus 1 for a sub k plus 1. While a sub k is k over 4 raised to k times x plus 3 raised to k. So for rho, it would be the limit as k approach infinity of, so we have k plus 1 times x plus 3 times x plus 3 raised to k all over 4 raised to k times 4 divided by k over 4 raised to k times x plus 3 raised to k. So we can cancel this out, and then 4 raised to k. So we have the limit of k plus 1 over k times x plus 3 all over 4. So we are going to evaluate the limit as k approach infinity. So this would be a negative of k plus 1 over 4k as k approach infinity. So so if applying L'Hopital's rule, this would be 1/4. So if we have x plus 3 over 4, so if it is less than 1, So it would be convergent. But if it is outside, if it is greater than 1, so it would be divergent. And if it would be on the boundary equal to 1, it would be inconclusive. So we have to try another test. So we have x plus 3 over 4 in between -1 and +1. So that would be um, the interval or the inequality testing for the convergence. Now for the boundary, we have to double check on that boundaries. So to get the interval of convergence, so we have x plus 3 over 4 in between -1 and +1. So we have x plus 3 over 4 equal to -1. So we have x is equal to -3 minus 4. X equals -7. While for x plus 3 over 4 equal to 1, so we have x is equal to 4 minus 3. So x is 1. So we have from -7 to +1 centered at -3. So the way to determine the convergence at these endpoints is simply to plug them into the original power series and see if the series converges or diverges using any test necessary. So when we use -7, so let's check what would happen to the series when we plug in -7. So we have -1 raised to n times n over 4 raised to n, and then we have x plus 3. So -7 plus 3 is -4 raised to n. So we can cancel out 4 raised to n, and then -1 raised to n times -1 raised to n. So that's +1 raised to n times n. So this is approaching infinity. So it is divergent. So that means at -7, it would be an open interval. So we are not going to include -7. But at 1, so when we plug in x plus 3 at x equals 1, so we have 1 plus 3, so we have 4. So plugging it in, so we have -1 raised to n times n over 4 raised to n times 4 raised to n. So we can cancel this out, and we have -1 raised to n times n. So it would now be an alternating series. But n is not approaching 0, and this is not decreasing and not approaching 0. So the alternating series is divergent. So in this case, the power series will not converge for either endpoint. So that's why it is an open interval from -7 to 1. So the radius of convergence is 4. It would be the distance from -3 to 1, so that's 4. R is 4. And the interval of convergence is from -7 to +1. Let's determine the radius of convergence and interval of convergence for the power series x minus 6 raised to n over n raised to n. So for this one, since both terms are expressed as a power of n, both numerator and denominator, we can rewrite it as x minus 6 over n raised to n. So we can now apply root test. So rho is the limit of the nth root of a sub k as k approach infinity. So this is the limit as k approach infinity of x minus 6 over as n approach infinity. So, limit of x minus 6 raised to n. So, we're just going to take the nth root. So, as n approach infinity, this would approach 0. So, meaning it is convergent anywhere. So, regardless the value of x in this power series will converge for every value of x. In these cases, we say that the radius of convergence is r approaching infinity, and the interval of convergence is from negative infinity to positive infinity. Now let's try to check for the radius of convergence and interval of convergence for the power series n factorial 2x plus 1 raised to n. So we can use ratio test. So your a sub k plus 1 is k plus 1 factorial 2x plus 1 raised to k plus 1. While your a sub k is k factorial 2x plus 1 raised to k. So your rho is the limit as k approach infinity of k plus 1 factorial is k plus 1 times k factorial, and 2x plus 1 raised to k plus 1 is 2x plus 1 raised to k times 2x plus 1 over k factorial 2x plus 1 raised to k. So we can cancel out similar terms and evaluate the limit. So since it is only k plus 1 remaining, 2x plus 1 has the variable x. So we evaluate this limit. So it would be approaching infinity. So the limit is infinite, but there is the term with the x's in front of the limit. So we'll have the limit is equal to infinity greater than 1. So provided that x is not equal to negative 1/2. So it is only the center that would make this element 0. So if we're going to have your 2x plus 1 equal to 0, so 2x is negative 1, x is negative 1/2. That is the center of convergence. So that's the only point where it would converge. So the radius of convergence is 0. So these are the items that we will be solving during our face-to-face meeting. Please prepare your answer sheets for this.